The case against the linked list is already on record. 3 lessons ago, we summed 17 million integers, twice. As an array, a few milliseconds. As a chain of nodes, nearly 2 full seconds. Every load a dependent miss. The prefetcher, blind. One streams, one commutes. And ever since, the list has been this course's cautionary tale. The anti-array, the structure we point at to show how expensive memory can get. But back then, I made you a promise, that the list has real wins, and that one day we'd weigh them properly. Today is that day. This lesson is the defense. And I'll give you the verdict up front, because the defense has nothing to hide. The list loses the default case. If you just need a sequence, the array wins, and the first module told you exactly why. But there are 4 specific situations, real ones, running in production right now, where the list genuinely beats it. By the end, you'll know all 4, and the more valuable skill, recognizing when you're standing in one. First, though, the defense introduces its client properly. So far, you've only ever seen it as a victim. Here's the whole machine. A node is 2 fields, the value you're storing and a pointer, the address of the next node. That's it. The list itself is just one more pointer, called the head, aiming at the first node. The last node's next pointer is null, end of chain. And critically, each node is allocated on its own, separately. The nodes of one list can be scattered across the entire heap, and in a long-running program, they are. That scattering is exactly what cost us 2 seconds back in Lesson 2. Now, 2 upgrades you'll see everywhere. Keep a second pointer to the last node, the tail, and both ends are reachable instantly. And give every node a second pointer, prev, aiming backwards. Now the chain walks in either direction. That's a doubly linked list. The price deserves saying out loud. On a 64-bit machine, every pointer is 8 bytes, and every node pays its own allocation overhead on top. A doubly linked list of small integers spends more memory on the wiring than on the cargo. Hold that thought for the verdict, because first, the surgery. Everything this structure is good at, it does with exactly 2 pointer writes. Say the chain reads A, then B, then C, and you want to insert X after B. Step 1, allocate the new node. Step 2, point X's next at whatever B was pointing at. That's C. Step 3, point B's next at X. Done. Read the chain now. A, B, X, C. 2 pointer writes plus 1 allocation. And here's the part to sit with. It does not matter how long the list is. 1,000,000 more nodes after C? Irrelevant. None of them were touched. Compare that to Lesson 3. Inserting at the front of a 1,000,000-element array meant shifting every single element. 1,000,000 moves to open one slot. The list does the same job with 2 writes. Order 1. Truly order 1. No amortized asterisk, no resize, ever. One detail matters more than it looks, and that's the order of the writes. X points at C first, then B points at X. Do it backwards, overwrite B's next before X knows where C is, and nothing points at C anymore. The rest of the chain is orphaned, gone. That one ordering mistake is probably the most written linked list bug in history, which is why the pattern needs to be reflex. Deletion is the same surgery in reverse. You route around the node. In a singly linked list, stand on the node before the victim and write one pointer, previous.next equals victim.next. The chain now flows past the victim as if it was never there. In a doubly linked list, it's even cleaner because the victim carries its own map. Its prev pointer knows who's behind it. Its next knows who's ahead. Wire those two to each other, 2 writes, and the node has unlinked itself. No walking at all. Now notice what didn't happen in either case. Nothing shifted, nothing reallocated. No block grew and moved house. Remember Lesson 3's sharp edge? One append past capacity, and every saved pointer into the array goes stale, dangling. The list has no such moment. A node's address is fixed the day it's allocated, and it keeps that address until the day it's freed, no matter what happens to its neighbors. Insert 10,000 nodes around it. Delete everything else in the chain. It has not moved. File that fact away. It's about to become Exhibit A. Now the cross-examination. Because that order 1 comes with an asterisk big enough to sync projects. Ask an array for element 500,000. Base address plus offset, 1 multiply, 1 add, 1 load. Order 1. Ask a list for element 500,000. There is no offset. There is no arithmetic. The only way to reach node 500,000 is to start at the head and follow 500,000 pointers. Order in, and every hop is a dependent miss, the expensive kind. So look again at the claim. Insert is order 1, if you are already holding the node. Getting your hands on the node is the part that costs order in. And this asterisk is a trap that has made entire code bases slow. The classic. Java's linked list lets you index it like an array. For I from 0 to n, process list.get of I. Looks linear. But get of I walks from the head every single call. 0 hops, then 1, then 2, n squared over 2. That's the painter from last lesson, walking back to the paint can on a structure people chose because they heard insertion was fast. The honest rule? A linked list earns its keep only when you never ask it for position I. Before the exhibits, one trick of the trade, because every serious implementation uses it and every interviewer expects it. Write delete by value naively, and the edge cases swarm you. What if the list is empty? Special case. What if the victim is the head itself? There's no node before it to route around. So, special case, rewrite the head pointer instead. 2 extra branches before the real logic even starts, and each one is a place to write a bug. The fix is almost cheeky. Allocate 1 extra node with no meaningful value and park it permanently in front of the head. It's called a sentinel, a dummy node. Now the real first element has a node before it, just like everybody else. The empty list isn't a special shape anymore. It's a sentinel pointing at null, same as any other list. Every delete becomes delete after. One uniform case, no branches. The standard library lists you'll meet in a minute are sentinel-based, and the kernel's lists bend the chain into a full circle through the sentinel, so even the ends stop being special. One cheat node, every edge case, gone. All right. The defense calls its first witness. Exhibit A, stable addresses. Open the Linux kernel source, and the most used data structure in the entire code base is a doubly linked list called list head. 2 pointers, next and prev, nothing else. And it's used in a way that looks backwards at first. The kernel doesn't put objects into lists, it embeds the list nodes inside the objects. The struct that represents a running process carries several list heads baked right into it. One links it into the global task list, another into its parent's children, others into scheduler queues, wait queues, timers. This is called an intrusive list, and it works for one reason: the fact we filed away. A kernel object's address never changes, so the same object can sit in 5 lists at once and leave any of them in order 1. 2 pointer writes, no searching, no shifting, no reallocation, ever. Could an array host that? Growth moves elements, and moving an element breaks every other reference to it. The same idea runs your memory allocator. Freed blocks of memory threaded into a free list with the pointers stored inside the free memory itself. The bookkeeping costs 0 extra bytes, and malloc hands out a block by popping the chain. Exhibit B follows straight from A. When something else hands you the node, the order in search disappears, and only the order 1 surgery remains. The textbook example, and a very real one, is the LRU cache, least recently used. Cached items live in a doubly linked list ordered by recency, freshest at the front. And a hash map points at each item's node. On every access, the map jumps you straight to the node, no walking. Then, surgery. Unlink, 2 writes, reattach at the front, 2 more. Order 1 to mark anything as freshest. Order 1 to evict the stalest from the tail. List and map, each covering the other's weakness. That structure is running in caches everywhere, and you will build it, hash map and all, in the patterns course. For now, just see the shape. The list is never asked to search. The kernel played the same trick for years. Its famous Order 1 scheduler kept a doubly linked run queue per priority level. So picking the next task, or moving a task between queues, was all pointer surgery. Constant time, no matter how many thousands of processes the box was juggling. That's the pattern. Some other structure finds the node. The list just does the splice. Exhibit C, predictability. Go back to Lesson 1's fine print on amortized analysis. The dynamic arrays appends are order 1 on average, but every so often, one append pays for a full copy of everything. At 1,000,000 elements, that one unlucky append moves megabytes. Usually you don't care. The math guarantees the average. But some code is not allowed to have an unlucky day. An audio callback that must fill the next buffer in a few milliseconds, every time, or the speaker pops. A game frame with 16 milliseconds of budget. A trading system where one slow message is a missed trade. In those worlds, the average is irrelevant. The worst case is the contract. And the list's costs are flat. Every insert, 1 node, 2 writes. Every unlink, 2 writes. No doubling, no copy storm, no spike, ever. One honest caveat. Allocating a fresh node on every insert has its own jitter, so real-time systems pair the list with Exhibit A's idea. A pool of pre-allocated nodes recycled through a free list forever. Flat costs, fixed memory, no allocator surprises. That pairing is quietly one of the most common structures in embedded and real-time code. The last exhibit comes from a different world. Functional languages. Erlang, Elixir, Clojure, the Lisp family, where data is immutable. You never modify a list. You make a new one. So think about what prepending costs under that rule. An immutable array would have to copy all in elements just to add 1 at the front. Last lesson's economics, all over again. But an immutable list? Allocate 1 node. Point its next at the existing list. Done. The old list is still right there. Untouched, valid, shared. The new list and the old list differ by exactly 1 node and share everything else. That 2-field node is the console Lisp was built on in 1958, and it's why every functional language made the linked list the list. 1,000 versions of a list, each one element longer than the last, occupy roughly the memory of 1, because they all share tails. Order 1 prepend. Perfect history. No copying. It's called structural sharing, and notice it's the same property doing the work yet again. Nodes never move, and here they never even change. So pointing into someone else's list is always safe. An array can't pull that off. A chain of frozen nodes can. Now, the verdict. And I owe you total honesty. In 2012, Bjarne Stroustrup, the creator of C++, ran a now famous benchmark on stage. Insert random values into a sequence, keeping it sorted. Insertion in the middle, that is supposed to be the list's home turf. The vector one. Not narrowly, and the bigger in got, the worse the list lost. Why? Because before every insert, you have to find the spot, and the find dominates everything. The vectors search streams through cache lines, prefetcher running ahead. The list's search commutes, 1 dependent miss per hop. And the vector's shift, the supposedly expensive part, is a bulk copy of contiguous memory. The operation hardware is best at. Java tells the same story. Linked list ships in the standard library, and Joshua Block, who wrote it, has quipped that he never uses it. The defaults agree. So should yours. There are middle grounds, though. The deck, an array of fixed-size chunks, cheap at both ends, no million-element shifts. That one is next lesson. And text editors split the difference with a gap buffer, an array that parks its spare room at the cursor. The middle ground usually beats both extremes. So, the ruling. The prosecution keeps the default case. A sequence you append to, scan, and index. Take the array. The cache wins, the prefetcher wins, lesson 2 stands. The defense won 4 narrow cases, and each one has a shape you can recognize. Addresses that must never move. The kernel's intrusive lists, the allocator's free list. Surgery on a node something else already found. The LRU cache. A flat worst case when one slow operation breaks the contract. Real-time pools. And shared immutable tails. The cons cell. Notice what all 4 have in common. Not one of them ever asks the list for element I. The moment you index, you've picked the wrong structure. That's the real skill here. Not array versus list as a debate to win, but recognizing which case you're standing in. Next lesson, the 2 structures you'll use most weeks of your career. The stack and the queue. The undo button. The call stack, the print queue, the message broker. All of them are one of these 2, and they're less structures than contracts. Push and pop. InQueue and DQ. Both the array and the list will audition for the job. The workhorses are next.